Okay, so in the previous videos, we learned two examples. We thought about two examples, and basically they share the same framework. And in both cases, what we obtained was beta 0 estimate and beta 1 estimate. So we calculate point estimates for them. And then we can calculate, re-enter the estimates back into the equation, and then you can calculate the value of y when x is given, right? So for example, like I would like to estimate the expected cost when I produce 10 units, right? Then you can put 10 here and put the estimates in at beta 0 and beta 1. Then you can calculate y as a estimated value. So we call that fitted value. We are going to fit y into x. By the way, in doing that, we assume the error term does not exist because error is error, right? We cannot predict that, and we assume error is on average 0. So we are going to ignore the error in prediction, right? So this is pretty straightforward. And for example, in the marginal cost, fixed cost example, suppose that simplify the numbers. Suppose that the fixed cost is 8.2 and marginal cost is 2.38. And then in this case, I would like to estimate the cost, total cost, when I produce 6.5 units, if possible. So 6.5 units is never been produced in our data, is never observed in our data, but not a problem in our, like mathematically, not a problem. Because just plug that in here. So if you produce 6.5 units, then for each unit, you are going to, each unit incurs $2.38 cost, and as a fixed cost, you have to add $8.2. So then, as a result, $23.67 is the total cost. So, as I said, without you never observe 6.5, but you can just choose any value of x and plug that into here using the estimates, then you can predict y. That is the prediction, linear regression prediction, right? So graphically, like from the dots, we made a trend line. We choose a trend line, then at any point, choose a point and then go straight up. Then it will cross the trend line. That point is the predicted value. This height, the height is the fitted value for the value x equals 6.5, right? Calculate that value. You can do it at any point, like at 10, at 3 point, something, whatever. So mathematically, that is really straightforward. Then I will ask you to do one simple example. Okay, then predict the total cost when x is 5 using these simple numbers. It's a pretty simple algebra, but please try it by yourself. Okay, it's pretty simple. The answer is 8.2 plus 2.38 times 5, right? Multiplication and addition. And the answer is 20.1. 20.1. Okay, so prediction, there is nothing like, of course, there is nothing special. Of course, this may be wrong. You need to understand that. It is just a prediction. Always possible, has a possibility to be wrong. Okay, so then, when you have predictions, now we just did a prediction for 5 units. What is interesting here is, let me show you the data. We already have an observation of 5, right? So you may compare the actual realization with your prediction. The prediction was 20.1. 20.1 is prediction, right? And by this way, you may predict all the existing observations, right? So if it is 1, you may use the prediction estimated results to predict y and then write that down here, right? So by that way, for each output, you have actual costs, observed cost, and predicted cost as a result. And obviously, they are different, right? Almost always they are different, right? Even if they are the same, that doesn't mean anything. Oh, that is good, but that could be still wrong. Anyhow, so you see two different y's for each output, for each observation. Then what you can do is take the difference. So I will call that residual. So when you assume x equals 5, then your prediction was 20.1, but actually our observation was 21, right? Here. So the difference is 0.9. So the actual cost is 0.9 above the predicted cost. So that is called residual. That much we failed to predict. So we define the residual in this way. So epsilon hat is the notation for the residual. So difference between the actual observation minus the predicted one, fitted value. The fitted value is used here. And by the way, this residual is used to calculate the standard error of regression, right? So as I said, to calculate the standard error of regression, you need to first estimate beta 0 and beta 1, right? So that's because to calculate the residual, you need to estimate beta 0 and beta 1 to calculate the fitted value. So they are kind of interconnected. Everything here is interconnected. Okay, so then graphically, from the dots, we make a trend line. That is the prediction, right? That's how we predict these guys. Still, there are differences. Those differences are residuals, right? So residuals at this point is the deviation, right? And of course, you can make a table. For each observation, you have one residual. So in some sense, you may understand the residual as a kind of transformed random variable. So the original random variables are x and y, and after a certain manipulation of those numbers, you get another set of numbers, as many as the observations. So that is also given in here. So there are 12 observations, and for each observation, Excel calculates predicted cost and residuals, right? So now we are going to use the residuals for further analysis. Residuals are more interesting theoretically, statistically, more interesting than just the prediction for now. So then, now, think about this decomposition. By definition, so this much was the fitted value, y hat. So, and remember, the difference between y and fitted value was the residual. So, the y actual value can be decomposed into fitted value plus the residual, and we may interpret the fitted value as the explained part. We could explain why this much using the regression model, but the residual is unexplained. So, of course, we would like to minimize this part, unexplained part. So small residuals imply all the dots are closer to the line graphically, or our prediction is more accurate. So you could explain more part of x. Or you may think the x and y are stronger relationship. So in chapter 11, we learned strength of relationship. That is coming up again. Because graphically, in this case, this is an extreme case where there is no residual at all. So perfect prediction means the correlation coefficient is 1. So this is the case where the strength is the maximum. Correlation coefficient is +1. And this like when you compare the left and right, this has smaller residual overall, but this has larger residuals. So in terms of prediction, this much is a failure of the prediction. So a large portion of y are not predicted. So this is better. The quality of prediction is better on the left side figure, right? Then we are going to use this idea to explain two things. First, earlier I said I am going to explain how the OLS is calculated. I did not explain how the estimators are calculated. Now I can explain that. So the idea is we are choosing the parameters to minimize the residuals. That means to maximize the accuracy of your prediction. So the parameters are designed to minimize the residuals. And second, you may evaluate the quality of your regression model, how much it explains, right? So we are going to think about these two topics. Of course, I'm going to go to the first one. So think about this, like back to the original. So so far we assumed Excel will calculate the estimators for us. But back in time, we need to think about how to do that. In other words, how to draw a trend line. I just give you the trend line, but how do we draw that? That is equivalent to estimating betas. And here is the idea, description of the idea. So the residual is calculated like this. So and the fitted value is based on the betas. That means if you change betas, when you your calculation of betas changes, then your residuals will change too, right? So then our idea is we would like to minimize these guys. I mean, we'd like to make the residuals not just minimize, as close to 0 as possible. So when I say minimize, it will go down to negative side. But what I'm saying by minimization is that we'd like to make it close to 0 as possible. That is what we want. To do that, we will take square of that. We will take square of epsilon. So, and then if to minimize the squared epsilon, you have to make epsilon close to 0, right? Epsilon squared will be minimized at 0 because quadratic function looks like this, so always minimize at 0. And because the residuals are many, there are many residuals, as many as the number of observations, we are going to add all of them. So overall, the total sum of square residuals should be minimized. We would like to minimize that. And this is called residual sum of squares or sum of squared errors. What's annoying here is different textbooks use different names and different abbreviations. That's really confusing and annoying. But let me follow the Excel. So Excel has residual sum of squares. So SS means sum of squares, residual sum of squares. So that is used here. So SS means sum of squares. Okay? Then that is 29.45. Right? So that is minimized by your estimators. Right? That means if you make a mistake in calculation, and if you happen to calculate another value for beta 0 or beta 1, then the residual sum of squares will be larger than what you get here. 29.459 is mathematically the minimum possible residuals, sum of square residuals, right? So that is mathematically how we calculate ordinary least squares. Automatically Excel does that, and of course in the minimization you can calculate the first order condition and verify the second order condition and solve the first order condition to calculate the optimal. That is how those estimators are obtained, and of course Excel does that for you. Okay, and the result is these numbers, right? As following these numbers, you will get the minimum sum of squared errors, right? I will use sum of squared errors. So, by the way, as an example, so the green line is the trend line that we used so far. But for example, you may think like something like this. Slightly change the numbers. So already we are using, say, like slightly change beta 0 at 8.1 and beta 1 at 2.4. I mean, so the optimal is 8.189 and 2.383. But let me try slightly different number. And then, this is green line. Green line is pretty similar to the true trend line, but its sum of squared errors is 29.48, which is slightly greater than 29.46. So, if you deviate from the optimal, sum of squared errors will increase. So your residuals will increase, and your prediction quality will be less accurate. And now let's try a totally different numbers. Like say beta 0 is 5, beta 1 is 3. So then it will become maybe another number like this, another line like this. And then your sum of squared errors will become 56. Increases a lot, right? So whatever number you try, the minimum is given here. This will minimize the residuals. That is how the estimator is designed, right? And then you may think, okay, so wow, computer is super fast in minimizing the sum of squared errors. That is actually not the case, right? So the computer does not do the minimization, but calculation is easier because beta 1, the slope, is related to the covariance or the correlation coefficient. So either way, so you may use covariance divided by variance of the explanatory variable, or correlation times the ratio of standard errors, right? So this is how how Excel calculates for you, right? Calculating these are not a big problem to the computer at all. And then finally, the intercept is based on the mean. So just the balancing out the mean is the job for the intercept, right? And then what you cannot calculate, if you have the data, what is the problem in calculation? The answer is none. You know how to calculate mean, sample mean, and the sample variance and covariance. You know how to calculate them, and you know Excel can calculate them. So I wanted to say that these guys are really easy to calculate for a computer, right? So in the example data, if you calculate the mean and the variance and the covariance, you are going to get these numbers. And then, based on those simple summary statistics, you may calculate the coefficient, the slope, as the ratio between covariance and variance, and also the intercept that matches the average, right? So simple formulas are available. Of course, you are not going to use that because anyhow, Excel will do that for you. Almost always, Excel or any other statistical softwares, any software will do this for you. So you don't need to worry at all. Okay, so in the next Okay, then let me give you this question at the end of this video. So now let's think about returns to education example. Here, the mean of X bar is 13.10 years. So average education is 13.10 years, and its variance is 6.36. And the average hourly wage is $7.77, and its variance is 33. The covariance between education and wage is 4.72. Using this formula, calculate the slope of this OLS estimator. Okay, so before watching the next video, please do this question and start the next video after you finish the algebra. Okay, thank you for watching. See you later.